So let's next have a look at stochastic processes. So the processes that we use to give mathematical description of the movements of stock prices. So you remember from your finance courses the concept of market efficiency. So particularly the efficient market hypothesis in its weak form specifically says that the current market price basically is all you need, in the sense that you don't need any information on past prices if you want to predict the future. So you cannot improve your prediction of stock prices by taking those past prices into account. In other words, the distribution of the future price, this probability distribution of future prices, that depends only on today's prices. So this concept in finance is actually closely related to a statistics concept, which is the Markov process. So a Markov process is a stochastic process, so an uncertain process through time essentially, where only the current value of the variable, of the thing that you're interested in, so a stock price, is relevant for the prediction of what the future might be. So what the probability distribution of future values of this variable might be. So it doesn't depend actually on how you got there, it only depends on where you are, what the next step in this process will be. So let's have a look at the simple Markov process. So let's consider some random variable, let's call it z. So and let's suppose that the z is going to move, it's going to move through time, and let's suppose that each year the change in this variable z will be some random number, epsilon, and this epsilon is going to be drawn from the standard normal distribution. So it's typically denoted by phi, zeros and mean zero, distribution with which is drawn from a distribution with mean 0 and standard deviation equal to 1. So if I know today's prices, let's call that z at time t, then next year's prices, so z at time t plus 1, will be today's price plus this standard normal variable epsilon. So that's how this variable moves through time. So each year there's a new increment of epsilon. So if this is what happens after 1 year, well, what would be the change in z after 2 years? So if you wait 2 years, how will z be distributed? Well, it's uncertain, right? So it's a random process, so we don't know exactly, but we know something about the distribution. Because what do we know? Well, we do know that in the first year there will be some standard normal distributed epsilon will be added to our z, and then in the year after that, again one standard normal variable epsilon will be added to that. But since this is going to be a Markov process, the second year change, the second epsilon that we'll add, is going to be an independent draw compared to the first year change. So there's two independent draws from the standard normal distribution that are going to be added to our variable z. So the total change after 2 years of our variable z is going to be the sum of two independent standard normal variables. So what do we know about sums of standard normal variables if they're independent? Well, first of all, this sum is again standard normally distributed. Its mean is going to be 0, the sum of the means in this case. So sum of the means in this case is actually 0. And variance of this new standard increment after 2 years is going to be the sum of the individual variances of each of these individual epsilons for each year. So each individual variance will be 1. So after 2 years, the variance will be 2. So change in our variable z after 2 years, we'll have a mean 0, will be distributed according to the standard normal distribution, to a normal distribution with mean 0, with a variance equal to 2. And if the variance is 2, then actually the standard deviation is the square root of 2, right? The standard deviation is the square root of the variance. So let's extrapolate this. Well, what happens after 3 years, or 4 years, or 5 years, or even after n years? Well, mean of this distribution remains 0, we keep on adding normally distributed epsilons, which each have a 0 mean. The variance is going to grow, so the variance after n years is going to be n. So that means also that the standard deviation of the difference in the change in z after these n years, that standard deviation is going to be square root of n. Or in other words, the standard deviation of this distribution that the z after n years is going to follow, to obey, the standard deviation is going to increase not proportionally to the time, but only to the square root of time. So that happens if you add up different normally distributed variables. So this is basically the key to what we call a Wiener process, also called Brownian motion. So basically what we did just now was we look at the change in 1 year, which was normally distributed, and then keep on adding a new epsilon for each year. But we can also make this time step smaller. And what we're going to do, or what's useful to do, Norbert Wiener did, who's the man you are standing in the photograph, what Norbert Wiener thought was, well, we can actually make these time steps a bit smaller. Let's take these time steps not equal to 1 year each, but a day, or perhaps even only an hour or a second, or even smaller. So what he did was, well, let's take the limit. As we take this interval, this time interval, smaller and smaller, going to 0. Well, these small changes that we get in each of these very small time intervals will still have mean 0. They will have a variance equal to the size of this time step, delta t, so it gets very small. The standard deviation of these time steps is going to be the square root of the delta t. And let's then take the limit of delta t going to 0. Well, this thing, if you do that rigorously, this is called a Wiener process or Brownian motion. So Brownian motion basically comes from the physics description of particles moving in the solution, for instance. So this Wiener process was, as I mentioned, invented by Norbert Wiener, who is in the photograph. So he's a famous mathematician, a genius, but also sort of the archetype of the absent-minded genius, absent-minded professor, if you wish. So lots of anecdotes about this man, so you can look them up on the internet. So if you Google Wiener and anecdote, you'll find lots of those. For instance, one of the colleague that he had, who had an office neighboring his, just down the hall in the corridor, and he used to come into her office often to have a chat with her. So they knew each other well. This situation persisted for quite a while, for years perhaps. But after a while, this lady, she moved office a couple of offices further down the corridor. And a little while after she moved to this new office, Norbert Wiener again strolled into her office, sat down at her table, and he introduced himself because he didn't recognize her when she had moved to this different office. So that's one anecdote about Norbert Wiener. You can find many more, as I just mentioned, if you Google him. So this process is Brownian motion. So what does it look like? So as I mentioned, what we do is we take this addition of a normally distributed variable, but we take the limit as the delta t, the time step delta t, as that goes to 0. So here actually I'm trying to do that in a picture. So in the top figure you see a fairly large time step. So if you close look at this graph, you see each time step will be 50 units of time in this graph. So after each 50 time periods, this graph makes a move, a random move. In the graph below that, I make this frequency of these time steps a bit smaller, and down below the lowest one, I do the same thing again, but now at an even faster frequency. So what you see happening here is that this graph becomes, it's still a continuous graph of this Brownian motion, but it's very jiggly, right? So it's definitely not a differentiable graph. So it's the time path followed by this Wiener motion, Brownian motion, this Wiener process is a continuous motion, but it's not differentiable. So it's very jagged function. Okay. So what we do in order to model stock prices is to model lots of different stochastic processes in nature as well. Is actually we use this Wiener process, this DZ or DZ, as a building block to build some more generalized stochastic motions of the thing that we're interested in, for instance, the stock price. So one thing that we can do is we can add a drift, a time trend. Let's call it A here, to that stock. So that would mean that the stock would actually move with a fixed speed, if you wish, upward speed in time A. But in addition to that, we also have this Wiener motion, so this uncertainty surrounding this straight deterministic motion. And we actually multiply this distribution by some sigma, which is going to be the volatility, essentially the standard deviation of these little jiggly random movements around this deterministic growth in linear growth in stock prices. So what will happen to this stock as? Well, it's going to move upwards at this speed A. So after time capital T, so after a larger time, the stock will be normally distributed. Its mean will have grown with the size A times this capital T. So that's this deterministic component, that's the deterministic growth of the stock. But this uncertainty from the second component, this Wiener, this Brownian motion component, that will have contributed to uncertainty, so to some randomness in this process, and this randomness after a time capital T will come with a standard deviation, this sigma, and this volatility, this width, times the square root of T, like we just covered. So that's Brownian motion with a drift, Wiener motion with a drift. And here you see a picture of that. So the dotted line is the deterministic motion. So we start at position 0 in this case, and you see that as time grows to the right, from 0 to 1000, slowly this object, this random variable is moving up until it reaches on average 2, the value of 2 after 1000 time steps. But the blue line incorporates also these random fluctuations. So what we see here is a linear motion, but with some randomness around this linear deterministic path. So this is Brownian motion with a drift. This is not quite what we want to model for a stock price. So stock prices don't have a fixed drift, but we're going to get closer. So we'll see in the next video how you model actually stock prices. And we get to the Black-Scholes formula for that.